Howdy, y'all. Welcome back to your chi-squared statistics videos. This video is going to go over chi-squared tests of independence. It's the last of the three types of chi-squared tests. If you hear music in the background, sorry, that's my brother. He's been heavily featured in these chi-squared videos. Okay, so I'm hoping that you've already seen the homogeneity video. This video is going to be pretty quick because you run the tests almost exactly the same for independence as you do homogeneity. There's only a couple of differences between them, to the point where your calculator only has the goodness of fit test and the two-way test. And you use the two-way test for both homogeneity and independence. So the main differences between homogeneity and independence come in the reason that they're conducted, right? Or how the tests are conducted, meaning like how the data is gathered. And then the way that the hypotheses are written. Other than that, it's the exact same process as homogeneity. So if you remember from homogeneity, the point of those tests is to figure out how changing one categorical variable will affect the distribution of another categorical variable. Okay. For independence tests, the goal is to see if two things are independent. Like if, in the example that we're going to do here, is hair color and eye color independent, not how does hair color affect eye color, because that doesn't make sense, right? So the way that you'll be able to tell if it's independence is that the problem will talk about one sample being taken and the subjects are classified later. Right, so it's more like a survey, like an observational study. But most of the time you'll be able to tell because the question will ask, are these two variables independent, right? Pretty easy, okay? So the only other thing that's different, like I said before, is that you have a difference in the way that you write the hypotheses. So in the homogeneity tests, we were talking a lot about like this variable affecting this other variable, or whether there is a difference or is not a difference between these. Okay. For independence, you have to phrase it a little bit differently. Okay. So for your null hypotheses, you would say that there is no association Okay. So there's no association between categorical variable 1 and categorical variable 2. So like there is no association between age and favorite TV show, for example. Okay. Another way you could write that is that variable 1 and variable 2, so categorical variable 1, categorical variable 2, are independent in the population of whatever the actual population is in the problem. Okay, so our status quo when we're talking about independence is usually to assume that things are independent, right? And then we have to prove otherwise. We have to prove that one variable has an association with the other. Okay, so your alternate hypothesis is either you would say that there is an association between the two variables, whatever they are. Okay, and then, or you could say these two, the two variables are not independent. So, for example, in the one that I just made up about what was it? I think it was age and favorite TV show. You could say age and favorite TV show are not independent in the population of Valley High School students, for example. Okay. Other than that, the test is exactly the same as homogeneity. Okay. We're going to run it exactly the same. Enter your matrices, run the two-way test, write the expected values out the same way, all of that fun stuff. So give me a sec to pause my screen and get to the actual example, and then you can follow along. Do that one with me. See you in just a sec. All right, everybody. So here we are at our independence test example problem. So this problem is very simple. It's asking about are these two variables, so eye color and hair color, or hair hue, I guess. We want to know, are these two things independent? So we're just trying to figure out if there is an association between these two variables. I want to make sure I point out that we're not talking about cause and effect here. We're just trying to see if there is a relationship between these two variables. Okay. So I'm not going to write out all my hypotheses and assumptions, everything out on the right side of my screen, because I do have it there for you on the left side of your screen. So take a look at the left side of the screen. The question is, can you conclude that eye color and hair color are independent? Great. So I'm going to skip the parameter part because remember, you're referencing the parameters in the hypothesis because there's no symbols or anything. The reason we have to do the parameter part on all of those other tests is because all of your hypotheses are written with Greek letters, right? So you have to make sure that you note for the AP readers, especially, what those Greek symbols actually stand for in the context of the problem. Okay, so I'm going to skip the parameter step here, start with hypothesis. So remember, the status quo here is that there is no association or that these are independent, which is what I wrote for you right here. So your null hypothesis is that there is no association between hair color and eye color, or you could say hair color and eye color are independent in the population of girls, right? You would say in the population of, and then pick out the population from the problem. Your alternate hypothesis is that there is an association, right? So we're assuming not, we want to prove that there is between hair color and eye color, i.e. hair color and eye color are not independent, right? Meaning that there's a relationship between them, they're related somehow, okay? Then for your assumptions, you still have those same three assumptions. So this is a random sample. It says so in the problem. There are 100 girls total. So remember, you do 100 times 10, and I haven't written that out in most of these other ones. So I'll write this out for you guys here. So we would say 10 times 100 equals 1,000, which you then would say that's definitely less than the number of girls in the population. In the population. Okay. And then your last condition there is your large enough sample condition, or success fail. For remember here, it's expected counts. All you have to say is all expected counts or expected values are greater than 5. I know we have not actually calculated expected values yet. That's okay. Just say that they're all greater than 5 because most of the time they will be, and then you go on to the next thing. Okay. Next, we got to name the test. So this is a chi-squared independence test. And then you have to make sure you set your alpha value. So again, they didn't give us one. So always 0.05. Always, always, always 0.05 if they don't give you one. All right. So remember what I told you in the last one for homogeneity. Once you get here, you have to calculate expected values next. Stop. Do not do that by hand. In this problem, it would be fairly easy to do because there's so few categories. You'd only have to calculate 4 expected values. But if the calculator can do it for you, you might as well let the calculator do it for you. Okay, so let's head over to my calculator. So remember, with these, you have to do this as a matrix. Let me move this over just a smidge. Okay, you have to do it as a matrix. It's not a list, and you need to store it as a variable. So I did that already. Just as a refresh for you, to access matrices, you click Menu, Matrix and Vector, Create, and then Matrix right there. Okay. Then it'll ask you number of rows, number of columns. So this is a 2 by 2. I filled in the values, and then you have to get this little arrow to show up. The way you do that is you press Control, which is the blue button, and then the var thing. See, it says STO. right there. That'll give you that arrow. And then I stored it as, I called it hair because this one was about hair and eye color. So if I type hair now, hair is a variable. It's not just a set of letters. I can click it and there it is. So I know that it's stored. Okay. So now we're going to go and run the chi-squared test. So here's how you do that. Menu, statistics, all the way down to stat tests. And this is a chi-squared two-way test because there's two variables and it's happening in a matrix. Okay, then you have observed matrix. That's this one, hair. And you say, okay, run it, and there it is. Okay, there's everything that you need. Okay, so I'm going to look at the chi-squared and the p-value and all that fun stuff in a second. But right now, what I need is the expected matrix. I need to do that first. And fill those values in because you will have to provide that information. Okay, so the way that you access that, because right now you can't see it, is you press var, VAR, and you're looking for stat.exp matrix. That's what you want. And then press enter, and there are your expected values. Okay, so if I go back over here, and I have them filled in for you already. Okay, so give me a sec. Let me write those in, and I advise that you do the same, and I will see you in just a moment. Okay, so I went ahead and I filled in all of my expected values. Remember that you do have to show one example of how you calculated the expected value. So typically I do the first one, the top left corner. That's the easiest one. So remember, expected value is row total times column total divided by table total. So you would just say like expected value, and then you could say like example. And then that would be 43 times 54 divided by 100. And you show that you would get 23.22 when you did that. Okay, so there's your expected value example. Next, you need to make sure you show what the degrees of freedom are. So remember, degrees of freedom is number of rows, which is 2 minus 1, times number of columns, which is 2 minus 1. So that's 1 times 1, which is 1, which I'm hoping that you saw. If we go back to the calculator really quickly, see it right here. It says degrees of freedom is 1. Okay. All right. So let's go back over here. Very next thing you need is to show an example calculation for your chi-squared value. So, and again, I'm hoping that you saw when we went back to the calculator there that you have the chi-squared value already. When you run the test, it will give you this test statistic, but make sure that you do an example. So remember, it's observed minus expected. So 10 minus 23.22, all of that squared divided by the expected value, which is the 23.22. Okay, so there's one of the components, and then you just say plus dot, 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 and then you can say equals. And from the calculator, I got that the chi-squared value was 28.7057. Okay, so that's it for your test statistic. All right, that's it for our test statistic. So after that, we just have to do the p-value part. But remember, the chi-squared test already ran that for you. So I'm not going to go back over to the, well, no, I'll go back over to the calculator. So back over in the calculator, here you have it. It's p-val. And so it's 8.42 to the negative 8. So that's essentially 0, right? It's like 0.00000084. Like it's basically 0. Okay, so the way that you would write this, and I also have it on the left side of your screen there, okay, but the way that I would write this is I would say, what's the probability that, remember, it's always chi-squared, and then greater than, it's always greater than, and then you put your chi-squared value here, so 28.7057. So the probability that I get a value that extreme or more extreme is it was 8.42, and I'm going to round up, 426, and then I'm going to say times 10 to the negative 8, which you can say is approximately 0, which is definitely less than your alpha value. So for making our decision, we are going to obviously reject the null, and then we have our conclusion in context. So I have that, like I said, again, over on the left side of your screen. So because p-value is less than alpha, we reject the null. We say there is sufficient evidence to support HA, which states that there is an association between hair color and eye color. Or you could say hair color and eye color are not independent. Okay, so there is a relationship there. Like if you have brown eyes, you're less likely or more likely to have dark hair, right? If you have blue eyes, you're more likely to have light hair, vice versa. Okay, and then this problem in the actual question did not ask you to do a follow-up analysis, but it's a good idea to do so. So remember, in order to do that, you need to look at your comp matrix. So I'm going to go back to the calculator one more time, press var, and I want stat.comp matrix. Remember, that's the composition of your chi-squared value. I'm going to press enter, and then you just want to pick the values that are largest. So the largest value is this one in the top right corner. So that's the one that contributed the most. So the way that you would phrase this is that the combination of blue eyes and light hair contributed the most to the chi-squared statistic. So there is essentially the association between hair color and eye color is strongest for blue eyes and light hair.
All right, y'all. So here is one more chi-squared independence example for you. Okay, so on this one, I don't have any of the expected values or totals filled in to the chart. Once we get to that point, I will pause the video and fill all that stuff in. But what I would do honestly right now, even before we start, is go ahead and create your observed value matrix here and enter those observed values that you see, because then it'll be a lot easier for us to run the actual chi-squared test when we get to that point. Okay, so here, this is very obviously a chi-squared test of independence because they are asking if these two variables are independent, okay? But if they don't ask that in the actual problem, like if they don't ask, is there an association between these two variables or are these two variables independent? Another way that you can tell is if in the problem they talk about taking one big sample of data and then classifying afterwards. So like here, what likely happened in this scenario is that the college like just took one large random sample of like course ratings after the students turned them all in and then classified them into these categories afterwards, right? They didn't take individual samples for, say, like courses that were required and courses that were an elective. Okay. All right. So let's go ahead and write our hypotheses. So remember, for independence tests, the way you write your hypotheses is you either say there is no association between, and in this case, it would be course rating and reason, right? The reason for taking the course. Okay, another way you could say that is the course rating and reason for taking the course are independent. Okay, that's another way you could say that, right? Because that's our typical assumption is that that variables are independent, right? And we have to show that they're not, right? So our alternative hypothesis here is that there is an association between these two things, course rating and reason. And then typically you would just say like at this particular college. Okay, so let's go ahead, do A, check our assumptions. So randomness. Okay, I cut this off of the problem. They didn't state directly that it was random, but you can assume randomness. So you could just say like safe to assume random. Okay, now next is my 10% condition, which I can't really calculate without the total of people like involved here. So I'm going to go ahead and pause my video and I'm going to have you do the same to figure out what all of the row and column totals are. And if you would like to fill in those expected values, like if you've already run your chi-squared test. I'm just going to fill in the row and column totals though. So I'll see you back in just a second. Okay, so I went ahead and filled in all of the row and column totals. So in order to do my 10% condition, I need to do 10 times my sample size. So my total sample size is 140. So that's definitely less than the total number of possible college students. Okay, all right, and then my last condition, remember, is success fail / large counts. Okay, and we are just going to say all expected values are greater than 5. Okay, even though we haven't calculated them yet. N, remember, stands for name the test. So this is a chi-squared test of independence. Okay, good idea here to also set your alpha value. So they told us that they wanted a 5% significance level. So my alpha value is 0.05. Okay, and another good idea here is to calculate your degrees of freedom. So remember, degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So my degrees of freedom here is 3. All right. Okay. Now, once you get to this point, okay, if you haven't already done so, enter your observed values into a matrix and go ahead and run a chi-squared, just a chi-squared test. So it's not the goodness of fit one, it's just chi-squared test. Okay. And from there, right, get your matrix of expected values and fill those expected values in. Okay, so I'm going to pause my video again to fill in those expected values. I'll see you back in just a second. All right, y'all, so you should be able to see all of the expected values written on the table up there in pink. Okay, so now what you do at the test statistic part is just show one example of an expected value. So remember, you calculate those by doing the row total. So let's say I just want to do it for this first cell right here. So the row total is 63 times the column total is 27 divided by the table total, which is 140, right? And that gives you 12.15. Okay, so there's your one example. Okay, next comes your actual chi-squared value. So again, just show one example of how this came about, right? So it's observed minus expected. So for that first cell, it would be 12 minus 12.15 squared divided by 12.15. Then you do plus ... and then just say exactly what your calculator said, right? Just list whatever the chi-squared value was that your calculator gave you, which for me was 2.678. Okay. All right. So that's all you have to do with the test statistics step. Next is obtain p-value. So I'm finding the probability that chi-squared is greater than 2.678, which my calculator also told me when I ran the chi-squared test. So that value was 0.444, which is definitely greater than any alpha value that I could set. Okay, so we are going to end up failing to reject our null here. So that's my M, my make a decision. So I'm going to fail to reject the null. Okay, and then the very last thing you want to do is state your conclusion in context. Okay, so I would say because the p-value is greater than alpha, we fail to reject the null hypothesis. We don't have enough evidence to say that, and then go right back up to your hypothesis, that there is an association between course rating and reason for taking the course. Okay, so i.e. these two variables are independent. Okay, now the very last thing, which is not directly stated, like it doesn't ask you to do this in this particular problem, but it's usually a good idea to do. So you can go, remember, into your calculator and look for the comp matrix, remember that's what it's called, which shows you all of the contributions to the chi-squared statistic. So you can say like where there was the most difference between what we expected and what actually was observed. But typically they would only ask you to do that, like to do a follow-up analysis if you end up rejecting the null, because they would then want to know, like, okay, if we're going to reject the null, like which combinations of these categories do I need to watch out for? Which ones are contributing the most? Which ones are the most different from what we would expect? All right, y'all, so that is it for this video on chi-squared tests of independence, and I'll see you in the next one. Bye, y'all.